Hello viewers, welcome to video lecture on electric field lines and electric flux. I am Dr. P. Ramakrishna, Assistant Professor of Physics, GDC Kamareddy. These concepts forms part of chapter Electrostatics in Electromagnetic Theory paper of BSc Physics syllabus. Before studying field lines and electric flux, let us recollect the knowledge which we have gained in the lower classes. They are charges, that is introduction to charges, Coulomb's law, electric field intensity. Coming to charges. Charges, we know that electric charges are of two types, positive and negative. Like charges repel each other and unlike charges attract each other. That means whenever we keep two either positive charges or two negative charges close apart, then they will repel each other. Otherwise, if we keep a positive charge and a negative charge close apart, then they will attract each other. Another property of electric charges is total charge of universe is conserved. We cannot create new charge nor destroy the existing charge. Total charge of the universe remains conserved. Another property is quantization of electric charges. It means that charge on any substance cannot take any value. Only the allowed values are integral multiple of charge on electron. We know that charge on electron E is equal to 1.6 into 10 to the power of minus 19 coulomb. Here the coulomb is the unit of electric charge. Then the charge on any other substance will be either plus or minus 1.6 into 10 to the power of minus 19 or 3.2 into 10 to the power of minus 19 or plus or minus 4.8 into 10 to the power of minus 19 and so on. But we do not find charges like 3 into 10 to the power of minus 19 or 5 into 10 to the power of minus 19 on any substance. The next property of electric charges is Coulomb's law. We know that the force acting between two charges is directly proportional to product of their magnitudes and inversely proportional to square of the distance between them. That is F proportional to Q1 Q2 by R square. Or it can also be written as F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Here 1 by 4 pi epsilon naught is the proportionality constant. The value of this proportionality constants depend on the system of units we are considering. This formula is in the case of SI units. Here epsilon naught is the permittivity of free space. Next topic is electric field. Whenever a charge is placed in the space, there will be its influence up to certain region around it. The space of its influence around it in the space is called as electric field. The space around any charge in which it will influence other charges is called as electric field. Next one is electric field intensity. In electric field, at any point, the force experienced by unit positive charge is called as electric field intensity at that point, or simply electric force per unit positive charge. Mathematically, it is written as E is equal to F by Q naught. If we consider electric field due to charge Q and observing field intensity at a distance r from the charge, then electric field intensity is given by E is equal to 1 by 4 pi epsilon naught Q by r square. The unit of electric field intensity is Newton per coulomb or volt per meter. Sometimes electric field intensity is also called as electric field strength or simply electric field. Now let us discuss our topic, that is electric field lines. Electric field lines are also sometimes called as electric lines of force or simply lines of force or field lines. They are the imaginary path in the electric field along which a unit positive charge is supposed to move. Here the important thing to remember is, to notice is, they are not real paths, real lines. They are purely imaginary, along which unit positive charge will be moving. We do not find any road-like paths on earth, in electric field for the charges to move. They will be purely imaginary like air traffic. This concept of electric field lines was introduced by Michael Faraday. This is the photograph of Michael Faraday. Now let us understand some of the characteristics of electric field lines. First one is, they always start at positive charge and collapse at negative charge. If we observe this figure, let us assume that this is the positive charge and these lines indicate electric lines of force emerging from this positive charge. We notice that they are starting from positive charge. If we look at this figure, this is the negative charge. Here all the field lines are collapsing into this charge. We do not see any incoming field line at positive charge. Similarly, outgoing lines of force at negative charge. So we can say that electric lines of force always start at positive charge and end at negative charge. The next characteristic is, they always emerge perpendicular to charged surface. If you look at these figures, they are always emerging perpendicular to the surface. They are not moving in a curved path with different angle. The angle between the field line and the surface of the charge will be always 90 degrees. The next one is, they are very denser nearer to charge and they become rarer as we move away from the charge. This can be understood from this figure easily. If we look at this figure, these two are the charges. These two are the charges. Here this is minus charge, negative charge. This is positive charge. Field lines are coming from positive charge to negative charge. Okay. Now if we observe, nearer the charges, the field lines are very dense. They are more in number. but as we move away from the charges, the number of lines of force in the space are decreasing. That is nothing but they are denser nearer to charge and rarer at greater distance. Next property is tangent to the field line indicates direction of electric field. The purpose of drawing electric field lines is to understand the magnitude as well as the direction of electric field. Now the direction of electric field is given by tangent to the electric field line at that particular point. If we look at this figure, let us suppose that this is the red color sphere is the charge and this blue line is the electric field line. If we are drawing tangent to the field line at this point, the direction of tangent will indicate field direction of field. At this point, the field is acting in this direction as shown in figure. So, we can get information of direction of field line from direction of electric field from electric field lines. The next property is no two field lines will cross each other. We can look into this figure. We do not notice any two electric lines of force crossing each other. What happens now? The question arises, what happens if they cross each other? It means if they are crossing each other, let us suppose that at this point they are crossing each other with different angle, then we will find two different directions for electric field at the same point, which is an absurd, wrong thing, wrong concept. You cannot have electric field having two directions at a point simultaneously. Electric field will act only in single direction at a particular point. So we say that no two field lines will cross each other at a point. The next topic is magnitude of electric field is proportional to number of lines of force. That means here if we look at this third figure, the lines of force are more in number nearer to charge and they are few in number at a greater distance. The electric field will be stronger nearer to charge and weaker away from the charge. The magnitude of electric field is proportional to number of lines of force. Here from this figure we say that the electric field is strong at close distances to the charge and weak at far away points from the charge. The next characteristics of electric field lines is they do not form closed loop. These characteristics make electric field lines different from magnetic lines of force. Magnetic lines of force are continuous closed loop, whereas electric field lines are not closed in the sense that they emerge from positive charge and end at negative charge. They will not again run from negative charge to positive charge. Whereas in the case of bar magnet, if we look outside the bar magnet, the field lines will run from north pole to south pole, and inside the bar magnet they will run from south pole to north pole. As a whole, they will form a closed loop. They will form a closed loop. But in the case of electric field lines, it is not the case. So these are the characteristics of electric field lines. Let us have a quick revision of characteristics. They start at positive charge and end at negative charge. They always emerge perpendicular to the charge surface. They are denser nearer the charge and rarer at greater distance. The tangent to the field line indicates direction of electric field. No two field lines will cross each other. Magnitude of electric field is proportional to number of lines of force, and electric lines of force do not form closed loop. The next topic is, let us suppose that here I have developed a small animation showing how the electric lines of force emerge from each other. Let us assume that these two are two individual charges separated by greater distance. In the screen they appear that they are close to each other, but let us imagine that they are very far away from each other. They are not in the vicinity of each other. Okay, now let us first look at positive charge, how the field lines will. This small animation will show how the field lines will emerge from positive charge. Now we see that the field lines are emerging out, going out of positive charge. Let us have a quick look once again. Okay. Now let us see similarly how the field lines will move in the case of negative charge. Okay. It is observed that the field lines are coming into the negative charge. They are collapsing into the negative charge. Since we assumed that these two charges are very far away from each other, we notice that the field lines are exactly perpendicular to the charge surface. They appear coming in a straight lines. Here we are notice that the field lines are coming in the straight lines. In the previous case also we noticed the same thing. This is possible only when the charges are very far away from each other. Now let us see another animation. This is also created by me. It will show what happens when a positive charge and a negative charge are placed at some close distance. They are nearer to each other, placed nearer to each other. What happens? Now this animation will show how the field lines will be there when the two charges are nearer to each other. Now we see that the field lines are emerging. The field lines are emerging from positive charge and ending at negative charge. This direction shows that they are moving from positive to negative charge. Let us have a quick look once again. Now from this figure we can confirm the last characteristics. Here the field lines are always moving from positive to negative charge. They are not again moving from negative to positive. That is why they do not form closed loop. Now the next topic is electric flux. Electric flux is defined as number of lines of force passing through given surface held perpendicular to the direction of flow. That means that mathematically it is given as phi E is equal to E dot A, or it is also given as EA cos theta. Here phi E denotes electric flux. The subscript E stands for electric. Phi denotes just flux. In the case of magnetic flux, we notice that it is phi b, and E is the electric field intensity, A is the area of cross section. Electric flux is a scalar quantity, whereas these two, electric field intensity and area cross section, are vector quantities. It can also be written as Ea cos theta, where theta is the direction between electric field intensity and area vector. Its unit is given by Newton meter square per coulomb or volt meter. If we look at this figure, this this area element is oriented in such a way that it is the vector denoting this area element is parallel to the electric field lines. These arrows will denote electric field lines, whereas this blue arrow will denote area element. We notice that in this case the two are parallel to each other. That means theta is 0. So we notice that in this case the flux will be maximum. Here another thing to remember is vector of area element. The direction of vector area is always perpendicular to its surface. It will not be there in the surface. It will be perpendicular to surface. Now let us see another case where the surface area is rotated to some angle. Let us suppose that this is the electric field direction. This is the electric field direction. My right palm is denoting electric field. Right hand is denoting electric field direction, whereas left hand is denoting the surface area element. Now they are not perpendicular to each other. In the first case they are perpendicular to each other. Though they are appearing perpendicular to each other, the angle between area vector and the electric field will be 0. Since the area vector, it will be like this. It will be perpendicular to the surface. If we assume that this is the surface, the area element vector is denoted by perpendicular line to this surface. So this will form the direction of area vector, and it is parallel to the electric field. So we can say that the angle between area vector and the electric field is 0 in the case of first one. But in the second case, they are not perpendicular to each other. So they are making certain angle. In this case, the flux will decrease. This is the maximum flux. First case is for maximum flux. This is an intermediate value. If you look at another case, here it is assumed that the surface is held parallel to the field lines like this. It is held parallel to the field line. Now in this case, the surface area vector will be perpendicular to each other. That means this will be perpendicular to field line. So theta will be 90 degrees in this case. Hence we notice that 0 flux in this case. So here we have three figures. In the first figure, the area surface, the surface element is assumed perpendicular to the field. When the area is held perpendicular to the field, its vector, area vector, will be parallel to field lines. Theta will be 0, hence maximum flux is noticed. In the third case, here the area element is held parallel to the field lines. So the area vector will be perpendicular to the field lines. Theta becomes 90, hence cos theta is 0 and flux will be 0. What we understand from this figure is the flux will be maximum when the area element is held perpendicular to the field line. It will be 0 when the area element is held parallel to the field lines. It will have intermediate value, some value when making certain angle with the field line. Now, to have a better understanding about these concepts, you may look into these books. Introduction to Electrodynamics by David J. Griffith, Electricity and Magnetism by Edward Purcell, and so on. You may also look into these websites. These websites give better understanding about field lines and electric flux using animations. Now, let us see what are the possible questions on these topics in university exams. The first one is define electric field lines of force and mention their characteristics. Second one is define and explain electric flux. This is a numerical problem. How much electric flux will come out through a surface S is equal to 10J kept in electrostatic field E is equal to 2I plus 4J plus 7K. Here both are given in vector form. So we can find out dot product of these two, scalar product of these two. We will get the answer. The next question is why two electric lines of force never intersect each other. Okay, we have already discussed a reason for it. The next question is a charged particle is free to move in an electric field. Will it always move along electric lines of force? Now let us see the answer. When the charged particle is initially at rest in electric field, it will move along electric line of force. When the initial velocity of the charged particle makes at an angle with the line of force, then the resultant path is not along the line of force. Here we have to take into consideration the initial velocity of the charged particle. When it is non-zero, when the particle has non-zero initial velocity, the path may not be in along line of force. It will make certain angle. Next one, the electric charge of any body is actually a surplus or deficit of electron. Why not protons? Many students will ask this. Even proton has positive charge. Why don't we consider deficit or excess of protons as charge? Let us see the answer. Electrons are loosely bound to atoms and can be readily exchanged during rubbing. Protons are strongly bound inside the nucleus. They cannot be easily removed from the atom or nucleus. Hence, electric charge of anything is just a surplus or deficit of electrons, not protons. It is very difficult to remove or add. It will become nuclear reaction if we try to remove or add a proton to any other atom. So, in the case of electric charge, we consider only either surplus or deficit of electrons. Now observe this figure. Here this one is positive charge and this one is negative charge. Can you guess why the field lines are looking different from the earlier figure? It is because the magnitude of charges are not equal. They are of different magnitude. Now let us see the question. Figure shows that the electric field lines near two charges. What is the ratio of their magnitude? Now this is home assignment for you. How do you find out the ratio of charges from this figure. Okay, it is easy from counting. Next is sketch the electric field lines at long distance from the charges as shown in figure. Here very small distance, it is these lines of force are drawn in the close vicinity of two charges. What you will do is you take a big paper, plain paper, and try to draw the lines of force at a greater distance also. From that you will gain the knowledge of electric lines of force. Next question. Sketch the electric field lines in the vicinity of two opposite charges where the negative charge is 3 times greater than positive charge. Now here what we notice is positive charge is stronger, negative charge is weaker. So many lines are coming out from positive charge, only few are collapsing ending at negative charge. In this question, it is given that the negative charge is 3 times the magnitude of positive charge. You are supposed to draw field lines. Now these two are the assignment questions you practice. We will give the answers for these questions in the following lectures. So this will end the topic of electric field lines and electric flux. Thank you for watching this video tutorial.